So we are going to talk about the performance surface in the uh, pretty much the response surface. So in this second part of the neural network lecture notes, first we're going to talk about the Taylor series expansion. So when we are approximating the functions, the function could be one-dimensional function or two-dimensional function or multi-dimensional function. So if we have a function, it only changes with respect to x, only one variable. Then we can do at a particular location, for example, at a location of x star, we can use Taylor series expansion to approximate the function. We can use the first order approximation, or you can do the second order approximation, or the nth order approximation. This is called Taylor series expansion. And for most of the time, we do the first order and second order approximation. And as we talked about before, if we go to NND, Neural Network Design Toolbox, if you look at the table of contents. So performance surface, if we look at Taylor series 1, this is a cosine function. And you see we can do this is a function. And order 0, order 1, 2, 3, 4. So those 1, 2, 3, 4, this is a function. If I click on a particular location, this will be my x star. At this x star location, I'm going to plot the original function as well as those approximations. For example, if I look at order 0, pretty much it's just y fx star. So fx star is just this term. If I continue one step further, you see this is fx star, this red line. And then if I add the first order, then I added the derivatives and approximation. You see this is a linear approximation. And if I added the second order, this is a second order. And if I added the third order, fourth order, you see the approximation. We call it accuracy or resolution will be a little different. Now, this is for the one-dimensional Taylor series expansion. The basic idea we are trying to convey to you is at a local area, you can use different kind of approximation, Taylor series approximation of the function at this local area. Okay. Now, but most of the functions, they not only just have one predictor or one variable, they might have multiple variables. Oh, up to now, this is still the Taylor series expansion in the one dimensional. So here, in this example, we're talking about cosine x. But here in the slide, we're talking about we have a function exponential minus x. Now Taylor series expansion about x star equals to 0. X star equals to 0 is at this local area. Then we can approximate with fx star and plus first derivative x minus 0 and second 1/2 second derivative, and then x minus 0 square, and then third derivative. Okay, third order derivative, and then nth order derivative. So this will be the expansion. This expansion is at this location, x star equals to 0. So 0 order 0, 1. Order 1, 1 minus x. Order 1, 1 minus x. Order 0. And the second order is right here. Okay, this is second order. 1 minus x plus 1/2 x squared. So those are the plot of approximations, but this function is for the exponential minus x. Now in the vector case, when we talk about vector, we have multiple variables, x1, x2 to xn. So this is fx. You see x here is bold. So in this case, we are also going to do the order 0, order 2, order 1, order 2 to order n. But when we do the first derivatives, because we have multiple dimensions, we are going to do the first partial derivatives. Okay. Partial derivative with respect to x1, then we have this equation. Then you do the partial derivatives for all the n variables, and then the second order. Second order, you need to, for example, x1, x2, x2, x3. So that's why you have a lot of terms. You will have a lot of terms here. So instead of just writing this in this form, we put it in the matrix form. So in the matrix form, we have fx star, and then the first order derivatives, x minus x star. But this is a vector. This is a vector form gradient. And then this is another vector, two vectors multiplication. Then it will become these terms, right? And then we have second order. Okay, this is what we call derivative. We call it Hessian matrix. So this is gradient, and this is Hessian matrix. Okay, now let's talk about something called, so this is the first order, second order. If you are interested in looking at this, we look at it before, right? So this is a function. Oh, I cannot maximize. Using MATLAB, if you code the graphical user interface, you can disable people to maximize the window. This one is disabled. And also you can add things to this menu. You can create a menu for yourself. Now, this is a second order approximation. Now this is a function. This is a function, and this is a function. So what's the difference between these two functions, these two visualization? I think we talked about this before, and let me maybe who is available. Mohammed, what's the difference between these two?
So one is the contour plot of the function, and other one is the function in a 3-dimension as a function of x1 and x2.
Yes, so this one has x1, x2. And then what is the third axis?
Is the function value.
Yeah, this is a function value. But where is the function value over here?
It's the contour lines represent the function value.
Excellent, excellent. Now, if we are going to click, very good answer, okay? Good job. Now, if we click on here, now we have approximations. So what is, you see, if we click on X star at different locations, the approximation will be different, right? The approximation will be different. Now I have so what's this approximation? When we approximate, so basically, what are we doing over here? What are we doing is we know this function, and we're going to calculate the first order derivative, second order derivatives. Then we are going to have the gradient and Hessian matrix. And based on the gradient and Hessian matrix, we can explicitly write the function form of the approximation. Second order, this is second order. If I use order 1, you see this is order 1. And order 1 and order 2, if we put it in the different locations, you see order 1 and order 2 approximation, what's the difference? Can I ask, can somebody maybe give me some insights?
So the order 1 is the linear approximation of the function at a given point, and order 2 is the quadratic approximation.
Excellent. The order 1, you stop right here. And order 2, you include both of them. And we don't include order 3 because this is a multi-dimensional case, okay? So order 2, our approximation come to this point. Order 1, we stop at here. So that's a major difference. And why it keeps changing? Because our X star, the location of X star keep changing. It's okay. So now let's proceed. Siqi, is this clear? Any questions?
I'm good.
Okay. Now the next concept is called directional derivatives. If you have a gradient, obviously previously we have gradient along each direction, right? Each variable is each axis. So now you can calculate the derivatives along a particular axis. This is ith element of the gradient. Now second derivative, this is called curvature. Curvature of fx along xi axis. This is ii element of the Hessian. Now, what is the derivatives along a particular vector p? Okay, so this is you are projecting this gradient to a particular direction. And this one you are projecting the second order second derivatives, the curvature along a particular vector. That means derivatives, first, do you agree that derivatives has direction? Derivatives have direction. And then if you give a particular vector p has a direction, and then you project this to the unit, why we divide by the magnitude of p? Because we don't want the magnitude of p influence the projection. So we want to do a unit vector projection. We want to project the derivatives to a particular direction, but we want to make sure this is a unit vector. And same thing, because you did a p and a p here, so that's why you need to divide by the square term of the magnitude of p. Let's have a look at how this works. Directional derivatives. You see here, let's first finish this example. This is a function. And if we have a particular location, 0.50, the x star, and if we have a function p, obviously at this particular location, we have derivatives. So we can take the f and derivatives at a particular location, x equals to x star. Then we got a 1, 1. Then in order to see 1, 1 projection to this particular vector, then we have p transpose 1, 1, and then the magnitude of this vector. Then this is 0. So what does this mean? If you got the projection component is 0. These two vectors, they are
independent.
Yes, they are independent. And another more accurate term is
perpendicular.
Yeah, they are perpendicular to each other. And there is another term that is more accurate. What is that?
Orthogonal?
Yeah, that is
Orthogonal. Yeah.
Yes, orthogonal. Now, if you look at this one, you see this is where is 1, 1? This is what is this location? This is 0, 0, right? Here is 0, 0. And if we want to go 1, 1, this is 1, 1. And this direction is 1 minus 1. But the x star is at 0.50. This is 0.5. This is 0, right? And this is our surface. This is a function surface. This is exactly this function. Let me minimize this one. This function is plotted over here. And x star, where is x star? X star is right here. You see, this is x star. X star is, you see, 0.5 and 0. And where is the location? You see this location, this P This P is along this direction. Minus 1, is it a 1 minus 1? 1 minus 1, right? This is 1 minus 1. And this is 1, 1. So these two vectors, they are orthogonal to each other. So if you want to see the directional derivatives, okay? So which one is derivative? So at this x star, all these vectors, which one is my gradient? Is this my gradient? Or this one is my gradient? Or this one is my gradient? Which one is the gradient? So at a particular, you have a surface, right? If you stand here, where is your gradient direction?
Aren't they all gradients?
Perpendicular to the
Yeah.
function value.
Yeah.
Perpendicular to the function surface.
Yeah, perpendicular to this line, right? At this location.
Yes.
So it goes along the change direction because gradient means you're going to change in that direction. So this is your gradient direction. And a negative gradient direction will point to somewhere smaller, right? So if you stand here, you can go higher. For example, this is a valley, right? Is this a valley? And if you stand right here, if you walk along the gradient direction, what's going to happen? If you stand right here, for example, if you stand right here, if you go along the gradient direction, you are getting higher and higher, or bigger and bigger, or you're getting smaller and smaller.
Getting bigger.
Because you are walking along this direction, right? If you're walking along the gradient direction, then you are getting bigger. But if you walk along the negative gradient direction, what's going to happen? It's going to get smaller. Do you guys agree? Now, the directional derivative, what we are asking is your gradient is right here. You have another vector. And what is if you project this gradient to this vector, and what value you are going to get?
0.
That's 0, right? Because they are orthogonal. But if you project to this vector, it's going to be 0.5. If you project to this vector, it's going to be 1.0. If you project this vector, it's going to be 1.3. If you project to this vector, you're going to be 1.4. But if you continue to project, they are getting smaller again, right? Getting 0 right here again. So this is why we want to calculate the gradient, the directional derivatives. Because directional derivatives will be able to tell you how much how much do you have left in the particular direction for the gradient. Now, let's have a look at the minimal. We have strong minimal. The x star is a strong minimal of fx if a scalar delta greater than 0 exists, such that fx star less than, if you do the delta x, and if you do a little bit shift, everything is greater than fx star, f. For all delta x, such that delta greater than delta x greater than 0. This is a strong minimum. And then global minimum. Global minimum is x star is a unique global minimum for of fx if this is true for all delta x is not equal to, does not equal to 0. And a weak minimum, fx star is x star is a weak minimum of fx if it is not a strong minimum, and a scalar exists such that fx star less than fx star plus delta x for all delta x such that delta greater than delta x, this norm, greater than 0. Now, what is the difference between these three definitions? First, what is the difference between this one and this one? strong minimum and the global minimum. So from just from the definition, what is the difference? Rinsan, what is the difference?
The strong minimum has a scalar delta greater than 0, and it has a condition of that scalar.
I mean, delta x has to be less than delta for this to be true, right? But for this one, you don't have such a constraint. Is that right?
Yes.
Then what's the difference between weak minimum and the previous two? First, what's the difference between strong minimum and the weak minimum? It seems to be the same, right?
But strong minimum doesn't have an equality sign.
Yeah. So this is a major difference. This has an equality sign over here. This one is only less than. If you have equality sign, that means you could be a ridge, right? Now let's have a look at this. This is a strong minimum, strong maximum, global minimum. Because for this strong minimum, if you shift a little bit delta x, as long as you satisfy in this range, you're all okay. But if you come here, this won't be true anymore. So that's why delta x has a range delta. But here we don't really have weak minimum. And if we want to see a weak minimum, so here we have a weak minimum. You see this, we have a ridge line. Everything else is greater than here, but along the ridge line, everything is equal. Agree? And this is a vector example. Okay. This is a scalar example. So over here, you see which one is a strong minimum, which one is the global minimum. This one is, and this one. Which one is the strong minimum and the global minimum? Obviously, here is a strong minimum. Here is the global minimum. And this one, this line is a weak minimum. Am I making sense? So if no further questions, we will move on to the next slide. So what is the first order optimality condition? You see here, when we do the Taylor series expansion, we have the first order, second order term. Now, if you have delta x here, you see for small delta x, if x star is a minimum, implies that this multiplication, if x star is a minimum, then this term should be greater than 0, right? If you change a little bit, this part should be greater than or equal to 0. If this is greater than 0, then fx star minus delta x, this should be less than. So in this case, if you have a minimum, that means x star is not a minimum. Therefore, you have to make sure this gradient equals to 0. Make sure this equals to 0. Since this must be true for every delta x, then gradient has to be 0. So this is a first order optimality condition. That means your gradient should equal to 0. Then x star is a minimum. And then second order condition. For second order condition, if the first order is satisfied, that means here you have 0 gradient, first order 0 gradient. Now you can cancel this term. You only keep the second order term right here. Now, in the second order term, we still have delta x. A strong minimum would exist at x star if this term is greater than 0 for any delta x. Therefore, Hessian matrix must be positive definite. So a matrix is positive definite if Z transpose A Z greater than 0. That means this part has to be greater than 0. So this matrix, Hessian matrix, must be positive definite. This is a sufficient condition for optimality. A necessary condition is that a Hessian matrix be positive semi-definite. A matrix is positive semi-definite if this part is greater than or equal to 0 for any z. Now, let's have a look at an example. So this is the same function that we studied before. If we take the first order derivative, then we have delta x. You solve for delta x for this first order equal to 0, then you got x star. This x star, and then based on the x star, we are going to calculate the Hessian. This is not a function of x because this is only the second order. You see, you only have second order, right? You don't have more than second order. So this is not a function of x in this case. So is this one's definite or positive definite or positive semi-definite? To test the definiteness, check the eigenvalue of the Hessian. If the eigenvalue are all greater than 0, the Hessian is positive definite. You see, you do this, you guys recall the eigenvalue decomposition. You see A minus lambda I, and then you solve for lambda. You got the eigenvalue. You see, you have two eigenvalues. One is 0.76, the other one is 5.24. If both eigenvalues are positive, then therefore you have a strong minimum. Make sense? Now let's have a look at the quadratic function. This is a quadratic function. So far, we are all talking about quadratic. So why are we so interested in a quadratic function? Any reason why we studied a quadratic function? Haidong.
I think quadratic function satisfy the optimality condition, each term positive semi-definite, and also it has a unique for stationary point. So satisfy the first order condition.
That's excellent because quadratic has nice properties. Okay. And anybody else has any other thought? Why do we introduce a quadratic function?
Is it because it can help us solve like polynomials, like, functions like raised to high the powers? I don't know. It's just a guess.
That's right. This is you can do the polynomial approximation, but a polynomial cannot be can go beyond the second order. You can do the third order polynomials, fourth order polynomial. So why do we do the second order quadratic function? Of course, quadratic function has nice properties, right? You can see whether it's concave or convex. And based on the gradient and Hessian, you can tell. But why are we interested in a quadratic? This is because of what? Siqi.
I mean, for me, it comes so natural moving from the first order to the second order. So, because quadratic function is like the order of 2, right? And if we can, like, if that correct, I mean, I don't know. I don't know actually.
Maybe because we have a loss function as a quadratic in the quadratic form for neural nets.
Yeah, that's also a possibility, but we take so much time to talk about the Taylor series expansion. That is because for any complex function at a local area, you can approximate them very well with the first order is not sufficient, right? It's not good enough. But second order, sometimes they give you pretty good performance in the approximation. And but some people may argue you need to go to the third order or fourth order right? But second order is pretty, it has already give you, I mean, you can have very complex surface, but as long as you give me X star, in a particular local area, I can use the second order approximation to approximate it very well. Do you guys agree? We have seen this example, don't you guys? We have seen this example, right? At a local area, we can approximate it very well. Second order approximation. So you have a complex surface. You at this local area, you may not know what is the true surface, but in this local area, you can approximate it very well. For example, this local area. If you come here, this local area, you approximate it very well, right? And you can continue to explore the surface. So that's why we are interested in the second order, because second order approximate, because of the Taylor series expansion. So what I'm trying to say is because of the Taylor series expansion. And we often use quadratic function to do the Taylor series expansion or second order Taylor series expansion to approximate a local surface. If I'm making sense right now. Haidong, do you agree, or you have any further thoughts?
Yeah, I feel like second order is a kind of nice compromise between accuracy and efficiency.
Yeah, this is because of the Taylor series expansion. We often use the second order to do the approximation, and also second order as Haidong and many others like Siji, Marta, what you have said, they have very nice properties. Okay. So if you have quadratic function, you can always express the quadratic function as in this form. Why the quadratic becomes this form? Because this is a fx star, this is the derivatives, right? And then this is Hessian. So you can always express a quadratic function in this form, and you have symmetric A. So you have gradient, the gradient will become ax plus d, the Hessian will become A. Why? Because the useful properties of gradients, if you take gradient of H transpose X, this actually equals to the gradient of X transpose H. It is actually equals to H. And the gradient of X transpose QX, this is actually equals to 2QX for symmetric Q, because Q transpose equals to Q, symmetric. Now, eigensystems of Hessian. So you guys recall what is eigen decomposition? Ax equals to lambda x. A matrix multiply a eigenvector equals to lambda eigenvalue multiplied by the eigenvector. Recall that? So that's so consider a quadratic function which has a stationary point at the origin. Stationary point at the origin, then whose value there is 0, then fx equals to this one, right? And then perform a similarity transform on the Hessian matrix using the eigenvalues and the new basis vectors. So for each eigenvector, those are all the eigenvectors. And since the Hessian matrix is symmetric, its eigenvectors are orthogonal to each other. So B minus 1, B inverse equals to B transpose. Okay, this is a nice property. Its eigenvector are orthogonal to each other. Okay, now A prime equals to B transpose A B. This actually equals to lambda 1, lambda 2, lambda n. And so in this way, we have Ax equals to lambda x. So this is called eigenvalue decomposition. So we decompose this matrix A with the eigenvector B into a diagonal matrix, and the diagonal entries are all eigenvalues. And the eigenvalues can be bigger or smaller depending on the arrangement of the eigenvector. So for a matrix A, you will be able to have eigenvector, and along each eigenvector, you will have the eigenvalue. Okay. Now, if we we have the Hessian matrix. If we take the Hessian matrix, we calculate the directional derivatives along a particular Hessian matrix along second order derivatives along, this is second order, right? Along a particular vector P, but the second order derivative is A, because this is a quadratic function form and it's placed at the origin. Now we replace P with the eigenvector. Eigenvector is the basis function right here, the basis function. Now we represent P with respect to the eigenvector. That means you can use C times all the eigenvectors, you can derive P. In other words, any vector in the space, if you have eigenvectors, can be represented as the combination of eigenvectors. So P equals to BC. Now, if you put BC into this equation, it will become C transpose B and B. And this is eta, lambda, and the B transpose B, C. You see, B transpose B, this actually, they are orthogonal, right? B is orthogonal, eigenvector is orthogonal. So B transpose B is an identity matrix. And this is also an identity matrix. This is an identity matrix. So what you got is the C transpose lambda C, and then C transpose C. So what is left is only the lambda, because this is a diagonal matrix. Everybody agree? Diagonal matrix here. So it becomes lambda I Ci, and divided by this C transpose C. This is a sum of the squares of all C's. So the directional derivatives, if you project the second order derivatives along any vector P, okay, the directional derivatives will be between the minimal eigenvalue and the maximal eigenvalue. Now, if we take the largest eigenvalue and also the eigenvector, so if we set the P to be the largest eigenvector, then what you are going to get is C equals to B times P, and you see the representation, because P equals to Z max. So at a particular location, you should have a C. This C is at a particular location, because this C is a vector. It's like C1 Z1 plus C2 Z2 plus you see here you have C1 Z1 plus C2 Z2 plus dot 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 plus Cn Zn. Okay, and there is something in the middle is Z max, so that's why you have a 1 here, and if you have a, so that's why P, any vector can be represented as the combination of all the basis vectors. Here you are using the eigenvector as the basis vectors. Now, this C1, this vector, this is bold, right? So this is C1, C2, C3, C4, and C you have a C max over here, right? And then 0, 0. That means every Z will become 0. Only left is Z max. Z max left. Okay, and C equals to this one, then you put it inside, then you will be able to get the projection. The projection of your second order derivatives along the Z max direction, along the largest eigenvector direction, is actually the lambda max. So for example, if you have this response surface, obviously this is a two-dimensional space. You have two eigenvectors. And you see this is a lambda max. This is a lambda mean. The eigenvalues represent the curvature, second derivatives along the eigenvector, the principal axis. So you see here, you have the coordinate, and you also have the eigenvector direction. You see eigenvector direction. So what is the eigenvector direction? Eigenvector direction is the largest variation direction, the first largest variation direction, and then the second largest variation direction. If you guys did PCA before, PCA is actually the eigen decomposition. And you got the first largest variation direction and then the second largest direction. Now here comes a question. Along this is my surface. Which direction I have the largest variation? Why this one is lambda max? This one is lambda minimum. It seems that this one is pretty large, right? This is an elliptical shape. In which direction if you walk the same distance, it changes more. Come on, folks, this is a terrain. This is a surface, right? If you walk the same distance along the first eigenvector direction and the second eigenvector direction, which one changes the most? Or which one gives you the biggest variation?
The direction Z2.
Yeah, Z2 is Z2 give us the lambda max. And the lambda max, the largest eigenvalue. And the Z2 is the eigenvector direction corresponding to my largest eigenvalue. Along this direction, if I walk a little bit, I will experience more changes. So that's why this lambda is actually bigger. Now, for this one, let's have a look at this one. We actually see all the response surface before. We calculated the eigenvalues before. You remember in the regression examples, we talked about those kind of different surface. But it doesn't bother for us to look at it again. So this is my response surface quadratic function. And this is the second order derivatives. And then this is my Hessian. And this is the first eigenvalue, second eigenvalue. And the first eigen direction, second eigenvalue, eigenvector direction. You see these two values, they are the same. So the change along both directions, they are the same. And then the eigenvector is 1, 0, 0, 1. Make sense? Now, let's continue. Now, this is an elliptic form. You see, one is the lambda 1 equals to 1. The other one is lambda 2 equals to 3. Now, I'm going to have a question now. Let me see whom I'm going to ask. Yeah, maybe you guys volunteer. Just to tell me, this is lambda 2 or lambda 1? Muhammad, this is lambda 2 or lambda 1?
Lambda 2.
Oh, no, this is the eigenvector, but what I'm saying is along this eigenvector direction, what is your eigenvalue? It's a lambda 2 or lambda 1?
It's lambda 2
Why it is lambda 2?
because the change is maximal in that direction from the given value.
And also, what is a vector, eigenvector?
So it is eigenvector
This
1
is 0,
minus
0.
1, Z1. Yeah.
This is Z1?
This is 0, 0, and this is 1, 1.
Yeah, this is 1, 1.
Yeah.
Because this is 0, 0, right? This direction
Yeah.
is 1, 1, right? From 0 to 1, 1. And what is this direction?
It's Z1.
This is Z1, right? Because
Yes.
this is 1 minus 1, right? And along this direction, the lambda 1 equals to 1. That means the array, when you walk, it's a little bit flat. But if you go here, it's a little bit steep. You will have more variation here. Is that making sense? Now, let's have a look at this part. Now, you have a quadratic function. Now you express the quadratic function into this form. Now this is your Hessian matrix. Based on the Hessian matrix, you got a lambda 1 equals to 1, lambda 2 equals to minus 2. You have two eigenvalues. One is positive, the other one is negative. Now, my question is, now the surface become a, what is this surface? It becomes a saddle. Saddle means on one direction you are decreasing, the other direction you are increasing. Now, my question is, which one is lambda 1, which one is lambda 2? Same question. The variant, which one is lambda 1, which one is lambda 2? And also, which one is Z1, which one is Z2? These two, which one is Z1, which one is Z2? In the middle is 0, 0.
Z1 would be the top one.
Z1, this is minus 1, and then 1, right? And this is Z2, minus 1, and then minus 1. Excellent. So so this one is Z2, right? You are saying this one is Z1, correct? This one is Z2. So which one? Z1 is one direction. Z2 is another direction, the other direction. You have two directions, two eigenvector, right? Which direction you are experiencing more changes or more variations?
Z1.
But if you go Z1, this is lambda 1, right? This is lambda 2. And if you see the contour line, you have more contour line here. That means you Z2. I mean,
Yeah, so the one with more contour lines are experiencing more like change, more slope,
yes. And
faster, like fast, whatever that's called.
yeah. And that's very good. Devon, if you are going along this direction, you are falling down or you are going up?
You're falling down.
Yeah, you are going this way, right? And you are falling down. And if you're going this direction, you are going up, right? That means you are going up like this. But if you look at if you're going up, this direction is pretty flat, right? It's not very steep. But if you go along this direction, it's very steep. Agree? So this is how the eigenvector, and eigenvalue actually define the response surface. But this is only for quadratic function. This is an elongated saddle. This is a saddle. Come on, you are in Pennsylvania, and we have a lot of like horse and those kind of farm. If you have ever ride any horse before, and you see what is this saddle. So next time when you go for horse riding, just try to study the saddle, which one has the biggest eigenvalue, okay? Then you can connect with the mathematical model you have studied in this class. Now, stationary valley, this is another function, and you do the quadratic representation, you get the Hessian, and then you have lambda 1 equals to 1 along one direction, lambda 2 equals to 0. You see, lambda 1 equals to 1, lambda 2 equals to 0. What does this tell you? Martha, we have two vectors here. Now, my question is, which one is Z1, which one is Z2? Which one is Z1, which one is Z2? Here is 0, 0.
All right, the one that's going like down is Z2 because it's -1, -1.
Yeah,
So
this is Z2.
Uh-huh.
This is Z1, right?
Yeah.
And Z2, you have an eigenvalue 0. What does this mean?
Means you have no slope.
So if you have a positive eigenvalue, you are going up, right?
Yeah.
If you have negative, you are going down. But if you
Yeah.
have 0 along this direction, it's like a valley, stationary valley. And along this direction, you don't experience any change.
Yes, correct.
Agree?
Yes.
Now, let's summarize. For quadratic functions, first, why do we study quadratic functions? That is a question that I asked Haidong, right? Why do we study quadratic function? Because we are interested in the Taylor series expansion. We are particularly interested in the second order Taylor series expansion. Why? Because second order Taylor series expansion give us a reasonable approximation at a local area. Okay. And the quadratic function, Haidong mentioned that quadratic function has nice properties. So what we are looking at, all these things, they are nice properties. So if eigenvalues from all these examples, if eigenvalues of the Hessian matrix are all positive, then the function have a strong minimum. If eigenvalues are negative, we have a strong maximum. If some are positive, others are negative, then have a saddle point. And then if you have all non-negative, but some are 0, then the function either have a weak minimum or will have no stationary point. If all eigenvalues are non-positive, some are 0, then either have a weak minimum or have no stationary point. And the stationary point is x star equals to minus A inverse D. So here, why this stationary point equals to this? Rensang, why stationary point is this?
You can just solve the equation of the first derivative equals to 0.
That is because when here we know if you take the derivatives of this function with respect to x, you get this one, right? And then you set it equal to 0, then x star equals to, what will be x star? Rensang.
Oh, x star will be minus D divide A. So it should be
No. You should move this to the equals to 0, move D to the other side. Then on this side, you should multiply the A inverse. Then this becomes identity. On the other side, it's minus A inverse D, right?
yeah.
Okay, excellent. Good job. Am I making sense? So this is how we get the stationary point. And yeah, good job. Now, so far, we finished this part. We first talk about the Taylor series approximation, and then we focus on the second order. Then we study different kind of surface. Now, let's have a look at the performance optimization. if you have a surface, now at a local area, you approximate it as a quadratic Taylor series expansion or second order 2 Taylor series expansion. Now, how do you, based on your information, how do you run the optimization algorithms? Okay, now we have basic optimization algorithms. The first one is called gradient descent. Gradient descent, also called hill climbing. At a particular location xk, you want to change your direction a little bit with alpha k is a learning rate and along the direction pk. And then you come to a new location xk plus 1. And the change between xk plus 1 and xk is alpha k pk. So this is a new location. This is a previous location. In order to go from previous location to the new location, you need to add alpha k pk. Pk and alpha k. Pk determine which direction you go. Alpha k determine how far you go along that direction. Agree? Martha, do you agree? This alpha is a scalar value. This p is a vector. So this vector defines the direction. Alpha times the vector actually tell you how far do you go along that direction. So alpha becomes your learning rate. Pk is a search direction. For steepest descent, you choose the next step so that the function decreases. Obviously, we want to search for the minimum. We need to relocate to a new location that is smaller than my previous location. But we know we have Taylor series expansion. Taylor series expansion that fxk plus 1 equals to fxk plus delta k. Then equals to at the location approximately equals to fxk plus gk. Gk is the first order derivative delta xk. So what is this part? What is this part? This is order 1 Taylor series expansion. Agree? Now, this gk is the gradient. If we want a function to decrease, that means we want this one to be smaller than this one. That means this gk transpose delta xk has to be less than 0. But we know the delta xk, we define the delta xk equals to alpha k pk. Let's put it in. That means we have to make sure alpha k gk pk less than 0. But here we know that alpha k is fixed, it's a value, right? It's a magnitude. Gk at a particular location, we can calculate gk, and pk is our search direction. In order to make sure this one is less than 0, we can maximize the decrease by choosing pk, the search direction, to be negative gk. So this is the reason why we go along the negative gradient direction. So this slide actually tells us why do we want to go to along the negative gradient direction. So xk minus alpha k gk equals to xk plus 1. So the new location equals to the previous location minus the learning rate and the gradient. So the minus is you go along the negative gradient direction. Now let's have a look at an example. So this is our quadratic function. You see still the same quadratic function. Let's choose the location to be 0.5, 0.5. And let's suppose alpha equals to 0.1. Then we get the gradient, and the gradient equals to 3, 3. Now the new location, from this location, we want to, this is our initial location. From this location, we want to search for x1. x1 equals to x0 minus alpha. Alpha is our learning rate. And then g0. This g0 is the gradient at this particular location. Then we got the new location, 0.2, 0.2. at the new location, I put this value. I put this value into this equation. I will be able to get G1, right? Then I got G1. So G1 minus alpha G1, and then previous location, we got a new location. Then we continue. Then we continue to do this from this 0.5, 0.5. Is this 0.5, 0.5? You see, 0.5, 0.5, right? Then the first iteration, you come to 0.2, 0.2. This is 0.2, 0.2. And then the second location is 0.02, 0.08. And then you continue. You will reach this direction. And you use the same learning rate, 0.1. Make sense? So the stable, some of you, we tried to, I think last time, who asked me a question saying, oh, how can I make sure my learning rate is stable? Okay, so you see, this is a quadratic function form, and you got the gradient. And this is a gradient search direction, the gradient rule. And then you try to put the gradient, this gradient in this equation, and then you move these two together. That is alpha minus alpha I minus alpha A xk. Stability is determined by the eigenvalue of this matrix. So if you times Zi, this is the way we find the eigenvalue, right? So you have Zi minus this equals to 1. This, suppose this is my i's eigenvector. Then you have lambda I, 1 minus lambda alpha, lambda I, Zi. So this is the eigenvalue of 1 minus alpha A. In order to make sure this is stabilized, we need to make sure our eigenvalue are less than 1. Why we want to make sure our eigenvalue less than 1? Rensang, you are the first one on the top of my list. I keep looking at you on the space. So why do you want to make sure this one, the eigenvalue less than 1, the magnitude should be less than 1? If you are greater than 1, that means when you search the next one, you are not going to converge, you're multiplying the larger eigenvalues. So you want to make sure the magnitude is less than 1, then by derivation, alpha should be less than 2 over lambda I. But lambda, the eigenvalues, you have smaller eigenvalue, larger eigenvalue. You have 2 eigenvalues in this case. For example, those eigenvalues, right? Those eigenvalues, that means you need to use 2 over 3. Largest eigenvalue, where are we? Right here. So 2 over 3, you need to divide it by the largest one. So you get the smallest learning rate. You want to make sure your learning rate satisfies this condition, then it will be stable. The learning will be stable. So you want to get a converge, try to here, and then convert. Oh, it's like this. You see here, this is a Hessian matrix, and you got the eigenvalue. And alpha should be less than, this is the largest one, right? Should be less than 2 divided by 5.24. Should be less than 0.38. You see, if you take 0.37, you are okay. You get to the minimum. But if you don't take 0.38, you take 0.39, then you see you are going to have oscillations over here. So this is a requirement. Now let's have a look at the learning rule. Has different kind of learning rules. This is only one of them, right? This is xk plus 1 equals to xk minus alpha k gk. This is one of the steepest descent. This is a traditional steepest descent. Now we can talk about different variations of the steepest descent. The next one is called minimization along a line. You see here, we have fxk plus alpha k pk. What is this? Devon, what is this? Xk plus my search direction and then search magnitude. Where are you reaching? Originally, you are at the location of xk. After you search along the direction pk and with the magnitude alpha k, where have you reached? You obviously reached the xk plus 1, right? Agree? This is what we have right here. Xk plus alpha k pk equals to xk plus 1. So you actually reach the, this is actually fxk plus 1 equals to fxk plus delta k, delta xk. But delta xk is alpha k pk. In this way, if you take the derivatives with respect for this function for df xk plus 1 over d alpha k, you see here, Renzang, why do we take the derivatives with respect to alpha?
Yeah, because we wanted to find the optimal step length so that this function will have a minimum.
Yeah, because you want to take derivative with respect to this one, and so that this function and set it to 0, then you will be able to reach the minimum, right? So here we are taking derivative with respect to alpha k, not something else anymore, okay? Not dx versus alpha k with respect to the parameter, because we want to define which alpha we take. We found that because this is gk delta xk, where do we have alpha? Obviously, here gk doesn't have alpha, but only delta xk has alpha k pk over here. So alpha k got to get away, right? And then you only have the pk left. And here you have alpha k pk, and then what are you left? Because this is based on this equation, based on this one. Okay, you got 2qx. So what you have here is the 2qx. 2qx, but you have 1/2 over here. So you only have, this is alpha pk, and you have delta, this Hessian in the middle. And then you have pk here. And some of you may ask, why do you still have 2 pk? So you're supposed to only have 1 pk, right? So anybody can tell me why we have 2 pk here? Because the previous equation, we are taking derivatives with respect to x, but here we are taking derivatives with respect to alpha k. We have 2 alpha k here. We have alpha k squared, then it will become 2 alpha k. 2 and 1/2, they cancel. You only have alpha k left. Mohammed, do you agree? And then pk still got left, right? And here alpha k get away, because here you have 1 alpha k left because you have alpha k squared. Then solve this equation, set it equal to 0, then you solve for alpha k. Alpha k equals to this term divided by this term. So it's actually minus, you have minus sign over here, gk, pk, and the pk, ak, pk. The ak is the second Hessian matrix. So let's look at an example. So if you got this, then you got a P0 first. Now you are not minimizing the first one, you minimize along the gradient direction. So initially you minimize along the gradient direction, minus G0, you got this direction. Then you minimize, right? But along this direction, how far do you go? Actually, we derive based on this equation. We're trying to seek, if we know GK, if we know the direction we are going to search, and this is the direction we're going to search, and we will be able to calculate. Now the learning rate is determined by you. You are not using a constant learning rate. So this learning rate will be 0.2 based on the gradient you have, and also based on the search direction you are going. So if you are here, immediately you go to minus 0.1, minus 0.1. And then at this location, you're going to continue to get the gradient direction, okay? And then you search for how long do you go, and then you go again. So this one, you see this one actually goes much faster, because when you use the constant learning rate, you didn't minimize along a line. This is your gradient direction. If I draw the intuitively, if we draw a direction, this is a line. This is a gradient line, right? At this location, you have a line, you have a gradient line. Everybody agree? And along this gradient direction, you want to find out where do you reach the minimum. Then you want to find out, you know where, first you know where you want to search. You know the direction you want to search. But the previous slides, we're trying to find out, okay, along this direction, how far should we search? We want to find out alpha. So we find out if we do this derivation, choose alpha k to minimize this term, then we can explicitly reach the location, okay? That will minimize along this line. And then once you minimize along this line, you're going to minimize along this line, and then you minimize along this line. So this way you are much faster. The algorithm will become much faster than just the traditional steep descent. So, and also at the same time, successive steps are orthogonal. You see here, successive steps are orthogonal. Why? We're going to prove it. So if you take this one with respect to d alpha k, you got this one, because this is a delta of xk d over d alpha, xk plus alpha k pk, right? And then this is your gradient direction at xk plus 1, okay? And this is the gradient direction at pk, at xk. And then successive steps, they are orthogonal to each other because you are setting this equals to 0. This is very good, right? Make you search much faster. Now, so far we finished the minimization along the line through the adjustment of alpha k. Now let's have a look at Newton's method. In Newton's method, you see here, Newton's method, you still doing the approximation. Everybody agree this is a Taylor series expansion, right? Now take the gradient of this second order approximation, set it equal to 0. You directly find the stationary point. You just set this one, take the gradient of the approximation, set it to 0. Then obviously what are you left? what is left is gk plus ak delta k, delta xk. So you find that you have the optimal xk location. If you know Hessian, just by one step, you reach the minimum. So this is initial search location. You have the gradient, and you have the Hessian over here. This is your gradient at this location. Now, if you do the x1 equals to the initial location, A inverse, and then gradient, then you will be able to get minus 1.5. You see here, Newton's method, just by one step, you reach the minimum. Because your minimum is at this location, minus 1.5, minus 1, .5, minus 1.5, right? This is minus 1, this is 0.5. You see Newton's method. But what is the drawback of Newton's method? In Newton's method, you need to know A. You need to know Hessian. If you don't know A, if you don't know Hessian, you will not be able to go just one step directly find the minimum. So far, we talked about 3 methods. Traditional steep descent, just gradient approach, and then minimization along a line, and then Newton's method. Newton's method just directly takes the derivatives of the approximation, and then you try to find out delta SK directly. And then you directly got this line. So this is a long quadratic example. You have 3 stationary points. You see 1, 2, 3. Hello, folks. There are 3 stationary points. Where are they? Devon, where are they?
Like just
where is
vectors
X1?
or in the image?
On the image, on this image. These are the 3 stationary points. Where is X1?
Negative 0.4242.
Negative 0.42, negative 0.42, and then 0.42, this one, right? And then negative 0.13, 0.13, where is it? Negative 0.13, 0.13 is right here, right? So what is this point?
Is that like the initial point, maybe? I don't know.
This is stationary point. This is a saddle.
Saddle point, yeah.
Yeah, this is a strong minimum. This is, what is this one? Devon, continue. What is this one? This point is?
Global.
Global
No.
minimum. Yeah, global minimum. 0.55 minus 0.55. So you have 3 stationary points. And if you start here, you see if you use Newton's method, you approximate the second order approximation on this region. You actually try to find the minimum using the approximation you directly got here. If you plot it in the original surface, it goes here. And you try different initial conditions. You see they get into different stationary points. Sometimes you get here, sometimes you get here, sometimes you get here. And depending on where your initial condition is. So Newton's method works very well. And just by one step. And then second step, you can continue to approximate and then you do it again. Make sense? This is very nice. Let's have a look at the conjugate vectors. So here is a quadratic form of the equation or response surface. A set of vectors is mutually conjugate with respect to a positive definite Hessian matrix A. You see, PK, PJ, then we have A in the middle. If this equals to 0 and K doesn't equal to J, this is called a conjugate. These 2 vectors are conjugated to each other with respect to the Hessian matrix A. And if we have a set of conjugate vectors, okay, and it consists of all the eigenvectors. You see, this is our eigenvector because AZJ equals to, because for eigenvector, AX equal to lambda X. So AZJ equals to lambda J ZJ. So this will become lambda J because it's a scalar, you can take it to the front. And they are orthogonal to each other. Okay. So if you are searching along the conjugate direction, you are searching along the, not the, you see, if you search along those directions, right? the gradient directions. Instead, you can search along the eigenvector direction. So the eigenvector of symmetric matrix are orthogonal. So for quadratic function, we can get the first order gradient and also second order Hessian. The change in the gradient at iteration k, because in iteration k, you have gradient direction gk, delta gk. The change in the gradient is gk plus 1 minus gk. This equals to ax plus 1 plus d minus axk plus d. Basically, it equals to a delta xk. But delta xk equals to alpha k pk. Delta xk is the search direction. You have search magnitude and search direction. So the conjugacy condition can be written as alpha k pk. Alpha k pk is the search direction. And then transpose a pj. So you have delta xk transpose a pj. So the idea is, you see, but you see a delta xk. This is delta xka. So this will be delta gk transpose times pj equals to 0. That means if you want to find a good search direction, okay, at j, if you know the previous change in the gradient direction, you will be able to find a better search direction at two different locations, xk and xk plus 1. If you know the change in the gradient, you will be able to identify a better search direction, pj. This does not require the knowledge of Hessian. This is perfect. Although when we are deriving it, we assume we know Hessian. But once we come to this step, because this a delta xk equals delta gk, so immediately here, as long as we know the change in the gradient direction, changing the gradient, the change in the gradient. As long as we know the change in the gradient, and we will be able to find a better search direction. Most importantly, this does not require knowledge of the Hessian. There's no Hessian here. So in the conjugate learning or gradient direction, choose the initial search condition, because in the very beginning, you only have one initial point. You don't have actually the change in the gradient. So you just put it as the negative of the gradient. And then you choose the subsequent search direction to be conjugate. So the next search direction is the previous search direction. Okay. Oh, is the gradient at the current location plus beta k and the pk minus 1, the previous search direction. The previous search direction in the first iteration is p0 equals to minus g0. But the beta k is actually, you can use 3 different ways to derive beta k. Beta k can be delta g k minus 1. The gradient change in the previous iteration, and then gk in the current iteration. Okay, and then you can have gk minus 1, and then gk minus 1, gk minus 1. So the basic idea is to find out the change in the gradient and leverage the change in the gradient to find a better changing the gradient to find a better search direction. So up to this point, this gives us a conjugate idea. Now let's have a look at the detailed conjugate gradient algorithm. So in the first place, you set it as the negative of the gradient. And then you select the learning rate to minimize along a line. So up to now, it's the minimization along a line. And then you search the next search direction using the iterative function because you know the previous search direction. And then the current gradient. And then the beta k is calculated based on previous gradient and the current gradient. And then you got the new search direction, pk. So this is the new direction. If the algorithm has not converged, return to the second step. You continue to do it. A quadratic function will be minimized in n steps. For example, here, this is a quadratic function. Initially, we started at 0.5, 0.5, and we got the gradient. This is our gradient. And then the initial search direction is a negative of my gradient. Okay, so this is my search direction. And then we use minimization along a line. We find our learning rate. And then we find the new direction. This is minimization along line. Minus 0.1, minus 0.1. Then once we got the minus 0.1, minus 0.1, we got the new, you see, this is a minus 1, minus 0.1. Minus 0.1, minus 0.1. We got the new gradient at G1. This is a new gradient. Then based on the new gradient, I find the beta. Beta is the current gradient and the previous gradient, the ratio. And then you got 0.04. Now P1, the new search direction is minus G1. This, you see the new direction. It's still along the negative. Please note, Ren-san, you see here, you're on the top. So this is a negative gradient direction, but it's not a strictly negative gradient direction. You actually adjust it a little bit based on what? Based on the beta 1 and the previous search direction. So you tweak a little bit. You don't go directly along the negative gradient, but rather you add a little bit of deviation. Then you got the new search direction. Based on the new search direction, you find the minimization along a line alpha 1. Then your minimization along a line, and then you got the new location. So this is a steep descent minimization along a line, and this is a conjugate gradient. Why the conjugate gradient is missing? But don't worry, I'm going to show you right here. Conjugate gradient, right? Conjugate gradient. This is there's no conjugate gradient. So first, let's have a look at a gradient. You see, this is a learning rate. Learning rate is click anywhere on the graph to create an initial guess. Then the steep descent trajectory will be shown. You can reset the learning rate using the slider below. A new trajectory will be shown. Experiment with different initial guess and different learning rate. So for example, I put it over here. And the learning rate, this is a negative gradient direction. And then you have a learning rate. This is how far you go. You are not minimizing along a line yet. You just, depending on this, however you can adjust, you see? You can adjust. You see the learning rate keep changing, right? And then you can keep increasing. That diverge. So when it diverge, this actually depending on the eigenvalues of your surface. 2 over lambda max. Remember, this is a learning rate. So this is steep descent. And we also talk about the Newton's method. This is a Newton's method. If you go here, you see Newton directly go here and then come back. If you go here, only a few steps, just one step, you got it. Depends on where you are. It's based on the Newton's method is actually based on the stationary, based on the, let's see the Newton's method. You just take the derivatives with respect to xk and set it to 0. Then the new direction equals to xk minus inverse, a inverse, and gk. Okay. Now let's go back to see the conjugate gradient. Now let's look at the steep descent. This is steep descent. and different learning rate steep descent for different function. And we can also see the method comparison. Here you see this is the conjugate gradient. Steep descent. Let me see. This steep descent it should be minimization along a line. You see, if you are here, you find the line, gradient line, and then you minimization along that line, and then you minimization again. You don't see any variation here. The two algorithms, this one is steep descent using the line search. This one is the conjugate gradient. You see the conjugate gradient. You see conjugate gradient, you don't actually, in the first step, you follow the gradient direction. In the second step, you actually don't follow. You don't follow the gradient anymore. You still follow the negative gradient over here, but you tweak it a little bit. This one go negative gradient, then it go overshoot over here, right? If you tweak it a little bit, you can directly shoot to the minimum. So that's the nice thing about. You see here, the first line, they are all negative gradient. They are the same. Initial search. And then when it comes to the second search direction, this is a conjugated direction. So it's still the negative gradient, but this is a negative gradient, but you tweak a little bit. You tweak it toward the minimum. That's the best thing about the conjugated gradient. Am I making sense? So these two comparison is actually what we should show here. Okay, this is the line search minimization along a line. But in conjugated gradient algorithm, we also minimization along a line. So I hope you guys don't just use the, of course, when you do the minimization, you can use the steep descent like this. You can fix the constant rate. But a better way to do it is to do the line search minimization along a line. Every time you find a gradient direction, you're trying to minimize along this line. Next time you have another gradient, you try to minimize along that line. Okay, this is a very basic gradient algorithms. Of course, you can do better. You can do the conjugate. You can do the minimization along a line. Obviously, in the conjugate gradient, we also have minimization along a line. Okay, hopefully by this point, I give you a good idea about different kind of gradient descent algorithms. Any questions so far?
I have a question regarding like in conjugate gradient, how do we choose like the beta values? Like where it came from, the logic behind it?
The logic behind it is right here. It's based on the proof. And beta has already been calculated. There's 3 different ways to do the beta. Okay. And most often used one is the second one. So if you follow this algorithm, in the initial location, you go the gradient, negative gradient, and then you minimize along a line, and then you find the next search direction, still negative gradient, but you use beta k to adjust a little bit based on the previous search direction. How do you get the beta k? Beta k is gk minus 1, gk minus 1. So it's actually right here. Negative.
So how do we derive, I mean, why these 3 expressions for beta k instead of like where it came from? That was the question.
This will take some time to do the derivation, but the detailed derivation is in the book. That book, what I told you, is electronically available online, neural network design. And you can review the corresponding chapter line. You will be able to find out the derivation for beta k. But here, what I try to do is to introduce you the algorithms. You can just use this result. And directly, for example, here, you use the results, got a beta 1. You directly got the new search direction. Make sense? If you are interested in the proof, go back to the book and then scan through that chapter and find the detailed proof, please.
Okay, thank you.
Mhm. Any other questions before we get into the back propagation?
I have a question, Dr. Yang.
Mhm.
So is conjugate approach is always better than gradient descent, or just it's at some point it's efficient? I just wonder.
Conjugate gradient is the best. Conjugate gradient is still gradient. It's still gradient search algorithms, but it's the best version of the gradient search. For example, in previous homeworks, when I ask you guys to do the gradient learning, I believe most of you used the constant learning rate. And then later you can minimize along a line. You use the improved algorithm. And then after you do the minimization along line, I think you converge much faster, because if you use constant learning rate, it might take like 1,000 iterations for this simple problem, or 100 iterations. But if you use minimization along a line, it may take maybe 10 to 20 iterations. But if you use conjugate gradient, it may only take you 3-4 iterations. It's reduction. So it will be more computationally efficient, and it's a better algorithm. Yeah.
Thank you.
You're welcome. Anybody else? Any questions before we proceed? Renzang, any questions?
Yes, so I have a question about the Newton's method. Because you are approximating the function locally,
Yes.
and does it guarantee that the approximated function bounds the original function?
Can you please repeat your question again?
So because Newton's method uses...
Yeah, we are using the approximation at a local area, xk, right?
Yeah.
And then this is our approximation. But the real function may not be this, right?
Yeah.
It's just that this local area, I do this approximation.
Yeah, so my question is, this local like quadratic function, does it bound the original function locally? Or it may have different like minimizers?
You're right. Newton's method, this is Newton's method, right? At this location, you see at this location, xk, I approximate the function like this. And then use Newton's method. Just by one step, I found where the, in this surface, I found where the minimum is.
Yes.
But when I reach this location, for the second iteration, I do another approximation. And then I use Newton's method again. Am I making sense?
Oh, okay. Yeah, I was always thinking about you have one step and you get the local.
No. You see there are multiple points here. You use over here, you use a Newton, you use the second order approximation, and then you find one point. And then once you reach this point, you use another, you do another approximation, and then you find another one. And then you find another one. Until here, I believe there is only 1, 2, 3, 4, maybe 4 iterations, you got the stationary point, global minimum. But please be cautious, because if you select the location differently, you have different approximation. And when you use the Newton's method, you may come to the saddle point, and you may come to the strong minimum or local minimum. So if you use Newton's method, you may do some kind of random start, and then you see which one is the global minimum. Make sense?
Yeah, but I think the same just happens to other gradient method, right? They were just stuck.
Yeah, that's right. That's right. It depends on what kind of surface you have. If your surface is already quadratic, already concave or convex, you can immediately find it, right? But if you have a super complex, like the surface that you guys simulated in the Gaussian process, in the Gaussian process homework, when you do the fractal simulation, obviously you have multiple complex surface. Then it's very hard for you to find a minimum. And you can use the Gaussian process to approximate the surface. So that one is called surrogate modeling, or it is called meta modeling. Here you use what? Here you use the quadratic function to do the approximation. In the Gaussian process sequential optimization, you use the Gaussian process to approximate the surface, and then you search the minimal. These two are the same thing. It's just that you use different function to approximate the complex surface at a local area. If you think about them, and if you try to collect them, and you will get a better understanding of the problem. Make sense, folks?
Yeah.
Okay. Any other questions? If no, let's move on. We talk about, first, I know some of you have already learned backpropagation, but I just want to present you my way of understanding through this architecture design. How do you see the backpropagation? Here we have a complex multi-layer perceptual network. I want you guys to be familiar with the notation. This R is the first layer, not a first layer. S1 is the first layer, S2 second layer, S3 is the third layer. So what does R mean? What does S1 mean? S1 mean how many neurons we have. You see, this is the first neuron, second neuron, and then we have S1 neurons. And then we have S2 neurons. So Martha, look, this is one neuron, second neuron, third neuron, and you have dot, 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 dot. So you have S1 neurons. You see here, you have 1, 2, S1, right? Here you have the subscript, not superscript. Superscript denotes which layer, and the subscript denotes how it belongs to which neuron. Make sense? So you have S1 neurons here, S2 neurons here, S3 neurons here. And then how many input you have? R by 1. This R is the input layer. So this is called R, S1, S2, S3 neural network. Make sense? And then you have N. N, what does N denote? N is a linear output. WP plus B equals to N. And then A equals to Fn. And this N2 equals to WA plus B, right? So this is an iterative function or nested function. It may be more accurate, nested function. And the last layer, the output will be, how many output is determined by what? We talked about this before. The variant, how many output is depending on what? The dimensionality of your output is depending on how many.
Was that the transfer functions?
Yeah, it depends on the transfer functions. Also, what is the dimensionality? It depends on how many neurons we have. Is that right? If you have one neuron, second neuron, each neuron will have output, right? So it depends on what kind of transfer function you use. That's right. You are very much right. Because if you use a different transfer function, it will change the output. The output depends on the transfer function. Also depends on how many, the dimensionality depends on how many neurons you have. Okay, excellent. So A1 equals to F1 W1 P plus B1. A2 equals to F2 W2 A1 plus B2. A3 equals to F3 W3 A2 plus B3. Make sense? So each layer has its own the weight and the bias. Okay, so if you nest them together, it will become this. Now the basic idea of backpropagation is you give an input, you initialize all the W and the B, and then you give it an input, and then this is called forward propagation. Forward propagation means You give me an input, and then I calculate my output, right? You randomly initialize all the W and the B, and obviously you can calculate your output. This is called forward propagation. What is a backward propagation? Haidong, what is backward propagation?
We are now going from the output layer to the input in a backward way.
Yeah, forward means you give me an input, I calculated the output, but my output may not agree with the target. You guys understand what I'm saying? Because you have a prediction and you also have your real value. They may not agree with each other. There are discrepancy. Haidong, is that right?
Yes, right.
If you have discrepancy, then based on the discrepancy, and then you can calculate the gradient. And the gradient can be back propagated back to all the weight. And if you know the gradient, obviously you can adjust your weight and bias, all the parameters. Then after you adjust the weight and the bias, and then you present the input again, you are not only just have one input, you have multiple input and multiple output, right? You have all the target values. So again, let me tell you, before I get into the details, you give input, you forward propagate, you got the output prediction, and the prediction doesn't match the real output, the target. And then you calculate the discrepancy. The discrepancy, based on the discrepancy, you calculate the gradient. And then the gradient got back propagated to each layer. And then based on the gradient, you adjust all the W and the B. And then you present the input again. And then you got output again. And then you, based on the discrepancy, calculate the gradient. And then you back propagate it again. And then you go for it. And then you fine tune until all the output prediction match or fit into the target values. Okay, this is very nice framework, right? Very nice framework. And it depends on what kind of function you have. And then your gradient calculation may be different. Of course, if you have a linear function, it's much easier. Now let's have a look at an example. This is a multi-layer perceptron. So for example, for this kind of classification problem, then obviously we need a decision boundary like this. So we need another decision boundary like this. And if it is in this direction, if it is over here, it is one, right? In the middle, then it's in another category. But how can we do that with a multi-layer neural network? You see here, this is a first subnetwork. We can get these two boundaries. You see the first boundary, it is a hard limit. You see, this is a P1, P2. This is minus P1 and 0 P2. That means 0.5 minus P1. Okay, it's equals to 0 is the boundary, decision boundary. So P1 equals to 0.5. P1 equals to 0.5 is the boundary. The second one is P1 minus P2 plus 0.75. That means P2 equals to 0.75. This is my decision boundary. Okay. Now, you see, this is minus 1, 0, minus 1, 0 with P. This is 0, minus 1, 0, minus 1 for the second neuron. Okay. And then you have a hard limit function, because hard limit give you, if it is above 0, it's 1, below 0, it's 0, right? So basically you're doing a 0-1 classification for these two boundaries. And you need to join both of them together. So only both of them are 1, then minus 0.5, you can get a 1. Okay, so this is AND operation. That means you need to be less than this and also less than this. Over here, then it becomes 1. So you have individual decision. This is the first boundary. This is the first boundary. Okay, second boundary. And then you need to join these two together. When you join these two together, you are actually designing this 1, 1 minus 1.5. And you actually design a design an AND operation. That means you need to, this one need to be below the second boundary and on the left side of the first boundary. Then you got an AND operation. So in this way, you got the first group, these two neurons and plus this neuron together, you create this decision, joint decision boundary. Now when it comes to here, and you need the third boundary. Third boundary is actually P1 equals to 1.5. No, this is a false boundary. This is P1, right? P1, P2, P1 equals to 1.5. P1 equals to 1.5. It should be this one. And then this is P2 equals to 0.25. It should be this one. So you have two boundaries here. This is a false boundary, and this is the third boundary. I think the marker, this one should be third. This one should be false. Okay, is that right? Everybody agree? Did I make any mistake here? Let me just type 4. And this one should be third boundary. Is that clear? This is third boundary, this is fourth boundary. 1.5, 0.25. And then you use another AND operation. You want to make sure in this area, you get a 1. And then over here, you get a 0. Now, you need to either this area or this area. So you need another OR operation. So you have two neurons and the other two neurons. This is boundary 1, boundary 2, boundary 3, boundary 4. And then for the second layer, you need AND operations to form these two boundaries. And then you need another OR operation. OR operation is actually determined by 1.5 instead of 1.5. 1.5, it will be AND operation. If you take the bias to be 0.5, it will become an AND OR operation. So you have 4 neurons. Here you have 4 neurons. Then you have 2 neurons. Okay, each neuron, this is one neuron to the end. This is another neuron to the end. This is the second layer. And then the third layer, you do an OR operation. Then either this one or this one. And then you do an OR operation here. You only have one neuron. Make sense? So in this way, you got the decision boundary. So MATLAB can, neural network can do a lot of this boundary, not just linear boundary. You can do any arbitrary boundary, MATLAB can do it for you. It's just it depends on what kind of operation you choose. So in the future, when you design the neural network, you got to design it, okay? You cannot just let a neural network, multi-layer neural perceptron, you just let it train. And you don't even know what's going on inside, okay? So that's why I don't like black box neural network training. Because when something works, there got to be a design behind it. If we just throw everything to neural network, and we are so irresponsible, right? And so we got to open the box and look at each neurons and design them, make sure they work as what we want. At least we should design all different kind of transfer function, or how many neurons we need and what kind of operation you want, based on the problem you have. Now, the first one, in these 3 slides, we are doing the classification problem. Now let me show you the approximation problem. Again, I told you guys before, neural network can approximate any function in the world. Okay? If you have any complex function in the world, it can approximate it. It is depending on how many neurons you use. Okay, and then what kind of transfer function you use. Sometimes you can use less neurons and you can do the job. And other students, they might use more neurons, they couldn't do the job. So a better understanding of how many layers and each layer, what you are going to use them to do to achieve what purpose. So let's have a look at the function approximation example. We are going to approximate this function. Then how are we going to do it? You see, you have a input, one input, then you have two sigmoid function, log sigmoid function. And then you have a linear layer, add these two sigmoid function together. And if you do this f1n equals to, this is a transfer function, okay? Log sigmoid transfer function. And then in the second layer, the transfer function is just a linear transfer function. Now, if we set the parameter like this, we will get a function like this. If we adjust those weight bias and weight and bias, you will get a different kind of function. For example, if you adjust the bias here, weight, second weight over here, you see, you can adjust the different variations. And I can show you an example right here, table of content. Is it back propagation, function approximation? Oh, this is not the one. It should be the network function. Yes, right here. You see, this is exactly, you have a P. This is your P. Okay, and now you're going to have two sigmoid function. Now the last layer is a pure linear. I didn't change it, just pure linear. Okay. Now, if you want to change the B2, if you change B2, what's going to happen? This is a W211. This is W212. This is B2. If I change B2, what's going to happen? Haidong, if I change B2, what's going to happen?
So we change the bias of the last up layer. So
you see, what does it happen? What does it happen?
So it's able
The graph
to
move.
What does it happen? You see, I have -2. What did you see? And if I move to 1, what do you see?
Y scale is changing.
Yeah, it is a parallel shift, right? You see here is a parallel shift. You're just shifting it. You don't change any function form. But if I change the W, what's going to happen? You see, what does it happen? It changes the shape, right? You see here, W. Make sense? Okay, if I change this W, what's going to happen? Oh, it's interesting. You see? So after you adjust the weight, pretty much you can adjust it into any function, you see? And then you can adjust this one. Or you adjust this one, this one, this one. Okay, interesting. Okay, so this is this one. But what I'm just trying to show you is neural network do the classification problem and also do the function approximation problem. Now let's have a look at the multi-layer neural network. We're going to look at the performance index. What is a performance index? Performance index is forward propagation. You have P1, T1, P2, T2, PQ, TQ. So what are they? Muhammad, what are they? P1, T1, P2, P2. What is P?
It's an input and output target pair.
Yeah, this is your P, right?
Yeah.
And then you have output T. This is a T, input and output target pair. Excellent. Input output pair, the training data. Now, obviously, your output is A. Now you are trying to see what is the difference between your target and A. Then you got an arrow, right? And then in the vector case, you do the arrow in this way. So this is called mean square errors. You're taking taking an expectation here. And I believe I asked you guys the sum of the squares and then mean sum of the squares, right? Mean sum of the squares of the errors, mean sum of the squares of the residues. So this is approximate mean square errors, a single sample. If you have a single sample. Now, this F is calculated based on your target data and also the output in the last layer. Obviously, in the last layer, you have output. Now, if you know the gradient of this F with respect to every W, because within here you have WB, WB, WB. If you know the mean sum of the square errors, and then you calculate the gradient with respect to all the W, obviously you can just use gradient descent. And you F with respect to each W, then you just use minus alpha, the gradient direction, minus alpha gradient direction with respect to B. You just take the derivatives with respect to each parameter, and then you use the gradient descent. But the problem is, I know my previous parameters I can randomly initialize, but I don't know the gradient. How do we calculate the gradient? So this is the idea. In order to do the gradient, obviously you can calculate the gradient. If you know the performance index, you can calculate the gradient with respect to this W and this B. And how are you going to propagate it back to this W and this B? But you can propagate back because this is a function of function, nested function. So that's why you see F of a W, but this NW is another function of W. So what we are going to do is we are going to use chain rule. You know, in calculus, we have chain rules, right? For example, you have Fn equal to cosine n equals to e exponential 2W. Then Fnw equals to cosine e 2W. Based on the chain rule, you can do Fn over dn, dn over dw. In this way, you got a df over dw. So this is why people design this multilinear neural network, because it gave us the advantage to do the back propagation of the derivatives. Now, application to the gradient calculation. You see, if you want to calculate this F over here with respect to W, you can calculate F, this performance index versus N. And then from N, you propagate it back to W, right? Because N equals to W, A plus B. So you can propagate it back. So this kind of chain rule will be able to help us. And then F over N, N over B. For example, this N equals to, in the M's layer, equals to the previous layer, how many neurons, right? NM equals to J equals to 1, S, M minus 1, NM. Let's see, NM, and basically equals to how many inputs you have. How many inputs is actually S2, right? Because the input to the third layer is the output of the second layer. The dimensionality of the output of second layer depending on how many neurons you have. So that's why we have how many input to this layer. That is the output of the previous layer. So WA plus B. So if you do the N versus W, it's actually just the A. And where partial derivative with respect to B is just a 1 because you don't have anything in the front. So in this way, however, the S, if we define F over N, you see, if we do F over N, this is actually the sensitive A equals to Fn, right? So if we do this, it depends on the function you are using, transfer function you are using here. So we call this F over N, call it sensitivity, because sensitivity depends on the transfer function. Then F partial derivatives with respect to W will equals to the sensitivity, and then times because the chain rule, right? F over with respect to N, then N with respect to W. Then this will equals to sensitivity times A. And then just the sensitivity, because this one is just 1. So up to now, it seems that the sensitivity value are very important. Sensitivity calculation depends on the transfer function. If we know the sensitivity, if we know A, obviously we know this, we use the gradient rule, immediately we can adjust for our new parameter values. So up to now, I only need to solve for this sensitivity. How do we get the sensitivity? Sensitivity equals to F over N. Now, next step, compute the sensitivity. The sensitivity, in order to calculate the sensitivity, we need to calculate the relationship between Nm plus 1 and Nm. If we go back, this is Nm plus 1, this is N2. So what's the relationship between N3 and N2? The relationship between N3 and N2, if you take the partial derivatives, it equals to this, right? However, this Nim plus 1 and Njm is actually equals to because N is actually the Wa plus B, okay? And then you take the partial derivatives with respect to N, previous N, you will get W, because this only Ajm is related to Njm. Because the output in the M's layer, is related to the input N here, only you have F here. So what we got is W, and then you got a F dot. This F dot is your transfer function. And then you got this diagonal matrix. So this Nm plus 1 with respect to Nm is actually just the weight times this matrix. So Sm equals to partial derivatives F over Nm. But F over Nm is actually equals to partial derivatives with Nm plus 1, and then Nm over Nm plus 1 over Nm. In other words, the sensitivity in the M's layer is related to the sensitivity in the M plus 1 layer. For example, the sensitivity over here is F over this N. And then the F over this N right here, F over M plus 1 and F over Nm. What they are missing is just the Nm plus 1 Nm. But Nm plus 1 over Nm is equals to F dot M Nm W M plus 1. So in this way, because this is Sm plus 1, we know the relationship between the M's layer, sensitivity of the M's layer, and the sensitivity of M plus 1 layer. If we know the sensitivity in the M's layer, M plus 1 layer, we can backpropagate to Sm's layer. If we know all the Sm, then we can calculate, use this equation just to calculate, adjust our weight. So the sensitivities are computed by starting at the last layer, starting from the last layer, and then propagating backwards through the network to the first layer. So Sm, the last layer, to Sm minus 1, to S2, to S1. Now, how to calculate the last layer? The last layer sensitivity is F over Nm. Because we know the performance index is T minus A, transpose T minus A. So why we have this? Because this is a matrix form of the sum of the squares of the arrow. And then we take derivatives with respect to n. This will become this tj minus aj square. You sum them together. Then take partial derivatives with respect to nim. Obviously, only ai relate to ni. So you got this term. And we know the ai, nm, it depends on the transfer function, right? Depends on the transfer function. And then you know the sim equals to -2 ti minus ai, then f dot n. So in this way, we calculate the sensitivity in the last layer. So if let me put it in a nutshell, okay? Forward propagation. In the first layer, you have an input, and then you put it in the nested function. You try to propagate forward, and then you got the output. And then your output doesn't match with the target. Then you got the F, okay? You got the performance index. Then you take the performance index, you see this performance index. And then you calculate the sensitivity in the last layer. Then based on the sensitivity in the last layer, using this equation, you propagate backward because you know the sensitivity in the last layer, you know the transfer function, you know the weight, okay, your current weight. And then you propagate it to the previous layer. And then once you finish the calculation of all the sensitivity, then you update all the weight. When you finish updating all the weight, and then you propagate forward again, and then next iteration, you do it again. So this just goes and until you learn and until it converge. So this, it's very important that we understand all the definitions, because this is a multi-layer, all the subscript, superscript. But the basic idea is as follows. It's summarized over here. You go forward, you calculate the discrepancy based on the discrepancy. So this is your discrepancy, right? Here, this is your discrepancy. Why I cannot highlight this part? Anyway, T minus A is your discrepancy. And then you got the sensitivity in the last layer. You propagate backward. And then based on the S, based on the weight, based on the A you have, this A is the output of the previous layer. Then you update all the weight, all the bias. After you update all the weight and bias, you forward propagate again, and then you back propagate it again, and then you continue to refine the process. And now let's have a look at the function approximation. Suppose you have this function. You have input and you got an output. So frankly speaking, you have a function, and then if you give an input, you get the output. But you want to use a neural network to approximate. That means if you give the input to the network, you got an output. You want to target from the real function and the predicted function, predicted neural network to be the error to be smaller. So you calculate the discrepancy, and based on the error, you fine tune the network. And then you keep giving it the input and output. You want to minimize the error. So from P, you got an A. And this is the neural network. Then how do we use the back propagation to fine tune our W and B? So this is the initial condition, W and B. Okay, you got this line is a network response, but this is a real data, and you couldn't approximate based on this set of parameters. Now you give it an input, give it a 1, and then you forward propagation. You do the forward propagation, and you got an A1. You give 1, and then you W A plus B, you got A1. This is your A1. And then you got your A2. And then you calculate the discrepancy is 1.261. Then based on the discrepancy, we are going to go back. This is transfer function derivatives, okay? The transfer function over dn, this is the log sigmoid function. It's actually 1 minus a1 and then a1. So the pure linear function, dn over n, it's just 1. So after we got this 1.261, we're going to leverage this transfer function derivatives to propagate back. Then based on the equation, t minus a is 1.261, and then we got this linear function. Linear function is just 1, right? Because the second layer is just pure linear. So this is just the 1. Then we calculate the S2. We got S2. Then based on the S2, we are going to propagate to S1. So we got a W2 and we got F. F is right here. We got F and we got a matrix. And then we got W2. W2 is the original value. This is the original value, initialized value. Now we back bracket it, we got S1. Now, once we get S2 and S1, we update W, B, W and B, okay? Now we continue to do it. And then this is our training. This is I equals to 1. This is our training. This is the original function, okay? So if the original function, this is our training. What do we have here? This is only 1, right? Original function is pi over 4 times p. Pi over 4 minus p, I equals to 1. So this is a function. Very easy, we can train this function. We can train neural network to approximate this function. If I equals to 2, then we have a much complex sine wave. Then you use this 131. You can still train the neural network, approximating the function very well. Then I equals to 4. But you got to know that the function you design, it has limitations. If you go even more complex, you will not be able to approximate. Neural network will not be able to do that. That means depending on how complex your curve is, you need to adjust the network structure. 131 network structure will not be able to approximate I equals to 8. Now, if we take this as 6, we use different network structure, 121. So people may be wondering, what is 131? Let's go back. You see, this is input is 1 dimension. So this is 1. And this is how many neurons you have? 2, right? And then you have 1 output layer. So this is 121 neural network. If you add another neuron here, this will become 131. Add another neuron, you have 141. Make sense? It's about how many neurons you place here, how many neurons you place here. Obviously here we try to adjust 121, 131, 141, 151. That means we keep increasing the neurons in the second layer. As you can see, if we keep increasing the neurons and the network capability will increase. That means this black curve, if you use 121, you cannot, no matter how you train it, you will not be able to approximate the function. Even use 131, you cannot do that. 141, it's okay, almost there. But if you increase to 151, you can do it. And the convergence, you see this, you can start from different initial values. And then the 1 iteration, 2nd iteration, 3rd iteration, 4th iteration, and then 5th iteration, you will be able to get it done. And this is a different initial values. You might not be able to converge. So sometimes you need some good initial values. So also you need to be attentive to the generalization. For example, you have a simple function. And if you use a simple neural network, it's okay, right? You train it with good generalization. Generalization means you don't have overfitting. But if you have a 191, if you have a super complex neural network, right? If you have 9 neurons in the second layer, you will have overfitting issues. For this curve, we don't have noise yet. But for some other data points, you will have noise. That means you're going to feed through every data point. So this is called overfitting. So there are some generalization ideas that you can use, for example, cross-validation. and Bayesian generalization idea. If you check the book, Neural Network Design, there's another chapter called generalization, different ideas to do the generalization. That means you need to have training data set, testing data set, and those kind of things to do the cross-validation. Okay, so this concludes today's this lecture about neural network. We actually talk about the performance surface, okay, and the Taylor series expansion, and also the gradient descent algorithms, different versions of gradient descent algorithms. Then we talk about multi-layer neural network, perceptual neural network, and then multi-layer neural network. How do we use backpropagation to fine-tune all the parameters? Okay, so this is end of this lecture.